So thanks for keeping for the end of this Diff-in-diff marathon. So Andrea said that because the paper I will present, I don't think it's going to take an hour and a half. So I'm going to do a quick overview of the last chapter of the book, which is not finished. So it's not the same level of completion as everything else, but it's going to be a nice connection with the paper in any case. So because now we're going to consider designs that are unrestricted. The treatment could be non-binary, could change several times, and you could have variation of the points in time at which the treatment is changing. And we're going to follow the usual roadmap. First, we're going to consider what the static two-way fixed effects estimator estimates. Then we'll go to dynamic two-way fixed effects estimator, and then we'll consider heterogeneity-robust estimators. So we're going to assume that while discussing the static estimator, we're going to rule out dynamic effects to be consistent with the implicit assumption made by the static specification. We are also going to assume that we have only two time periods, which actually is without loss of generality when you rule out dynamic effects, because you can show there is actually this recent, nice recent paper that shows that the two-way fixed effect estimator with many periods can actually be written as a weighted average of two-way fixed effects estimated with only two time periods. So we are again going to have, if we make the parallel trend assumption, our usual parallel trend assumption, we are now unsurprisingly going to get a decomposition result where the two-way fixed effect is unbiased for a weighted sum of effects where the sum of the weights is equal to 1, but some weights can be negative. Nothing new. Something that's interesting is that actually in that case, and a bit striking, I think, is that in that case, if dGT is strictly positive for every GT, so everyone is treated at every period, at least to some degree, then you're going to have that exactly a half of the weights in this decomposition are negative. Groups whose treatment increases more than the average from period 1 to 2 are going to be such that their treatment effect at period 2 is weighted positively, but their treatment effect at period 1 is weighted negatively. And for groups, the control groups whose treatment increases less than the average is going to be the opposite. Their treatment effect at period 1 will be weighted positively, but their treatment effect at period 2 will be weighted negatively. Okay, so lots of negative weights. I'm going to skip all this. So something a bit more novel to this chapter is that if you are really in a general design where at period 1, groups are potentially, many groups might already be treated with heterogeneous intensities, maybe a parallel trend assumption on Y0, the outcome without the treatment, is not the very natural parallel trend assumption to consider in that setting. Just for instance, if you have a third period of data that's available, period 0, then you're never going to be able to run a pre-trends test of parallel trends on Y0 because you don't observe Y0 at period 1 or at period 0. Okay. Now, what could be the case is that groups are treated with different heterogeneities at period 1. The treatment of some groups changes from period 1 to 2, but from 0 to 1, treatments do not change. Okay. Then in that scenario, the parallel trends assumption that you are going to be able to test via a pre-trends test is going to be this parallel trend assumption. an assumption on the counterfactual outcome evolution in the scenario where groups keep the same treatment between period 1 and period 2. Okay? A parallel trend assumption in the counterfactual where group treatment is not changing between period 1 and 2. So if that's the assumption that we want to make, then we are going to get a different decomposition for the two-way fixed effect estimator. It's going to estimate a weighted sum of effects where we could still have that some of the weights are negative. And essentially the groups that are going to get whose effect might be weighted negatively are going to be those such that that experience an increase of the treatment from period 1 to 2, but that increase is still lower than the average increase across all groups. If such groups exist, then we will have negative weights in this decomposition. Yeah. Now, for this type of quote-unquote unconventional parallel trend assumption, exactly like we did in the previous chapter to evaluate what Callaway co-authors called the strong parallel trends assumption, it's useful to see if this type of unconventional parallel trend assumptions, which type of implications they have when you combine them with the standard parallel trends assumption, the one on Y0. So we're going to do the same thing here to see if actually this type of assumptions don't have hidden undesirable implications. Let's see if this implies something that maybe was a bit unexpected if we combine it with the classical parallel trend assumption, okay, the one on the Y0. If we do that, then, and also we need to assume that we have at least one group that's untreated at period 1, then you can show, and that's actually what I show here, that together, parallel trends on Y0 and parallel trends in the counterfactual where your treatment is not changing, that's actually implying that the treatment effect is constant over time. Okay? So it's a bit similar to the strong parallel trend assumption we discussed earlier. When you combine it with the classical parallel trend assumption, it implies that treatment effects are constant across units. Here, the novel parallel trend assumption I was introducing, when you combine it to the standard one, it's actually implying that treatment effects have to be constant over time. Okay, which might not be a very plausible assumption, or at least it's important to keep in mind that if we work under this type of assumptions here, we are implicitly assuming constant effects over time. Okay, and then we could say, okay, now instead of assuming parallel trends, let's see if we can get a more positive result for those two-way fixed effects regressions if we actually assume that the treatment is as good as random. And remember that in the two previous cases we reviewed, designed with variation in timing, designed with variation in the dose, we had put that two-way fixed effects were estimating a potentially non-convex combination of effects under parallel trends, but not if we were ready to assume that the treatment was as good as random. Actually, this is no longer going to be true in general designs. In general designs, and that's a bit, I think, striking, even if the treatment is as good as random, you could have that your two-way fixed effect is not estimating a convex combination of effects. So specifically, so here I'm going to assume that the treatment is, the first difference of the treatment is as good as random in the sense that it's independent of outcome evolutions and of the period 1 and period 2 treatment effects. So, okay, now maybe let me just up. Yeah, so even if you assume that this holds, that the treatment path, your period, the vector of your period 1 and 2 treatments are independent of all the unobservables, namely outcome without treatment at period 1 and at period 2, and treatment effect at period 1 and at period 2, then you can still get that the two-way fixed effect estimator estimates this weighted sum of the treatment effects at period 1 and at period 2. Okay, so ST denotes the treatment effect at period T. And you could, and the weights depend on the variance of the treatment at period T minus the covariance between the two treatments. And you could have that, let's say at one of the two periods, you could have that the covariance is greater than the variance, and therefore the weight is negative. So there's going to be many cases where there's going to be some cases where the weights are all going to be positive. For instance, if the treatment is binary, or if the treatments are uncorrelated at the two periods, etc. But if the treatments are non-binary and the treatments are serially correlated, then you could have that even with a treatment that's as good as random, your two-way fixed effects regression could be estimating a non-convex combination of effects. And note that under this assumption, you don't need to estimate two-way fixed effects or first differencing the regression. You could just use a cross-sectional regression of the period 1 outcome on the period 1 treatment to estimate the period 1 treatment effect. And you could estimate run a regression of the period 2 treatment effect on the period 2 treatment to estimate the period 2 effect, and then average the two. So this idea that, even if you believe that you have random assignment, first differencing, just in case random assignment is not perfect, cannot hurt you. Well, actually it can, because you could have cases where you do have random assignment, so you would not need to first difference. And by first differencing, instead of, just estimating the ATE, you're going to be estimating one of those weird non-convex combination of treatment effects. Okay, and so then so in passing, in general designs, the most common method to estimate dynamic effects is to run what's called a two-way fixed effect distributed lag regression. So you regress YGT on group fixed effects, time fixed effects, and the current treatment and some of its lags. Okay, and that's, for instance, a regression that's discussed in the Engrist and Pischke textbook. And probably unsurprisingly for all of you at this stage, if treatment effects are heterogeneous, this type of regressions will not work. You're going to have that so this coefficient will estimate weighted sums of the effects of the health lag of the treatment with potentially negative weights. But on top of that, you will have the contamination problem that the coefficient on lag 2, let's say, is contaminated by effects of lag 1, lag 3, the current treatment, etc., etc. Okay, so now we're going to review heterogeneity-robust estimators, separating between two cases. So first, the estimators that we can use if we are ready to rule out dynamic effects, and then the general case that we will cover in the presentation, where we actually want to allow for where we want to allow for dynamic effects of the past treatment on the current outcome. So if you are ready to rule out dynamic effects, then in a paper with Xavier, in our AER paper with Xavier, we had proposed a simple estimator that we had called the DIDM, and whose basic idea can be presented in a simple two periods case where the treatment is binary. So in that case, the target parameter is going to be the average effect of the treatment among the switchers, namely all the groups whose treatment changes from period t-1 to period t. And then to estimate that effect, you're going to compare the outcome evolutions of the switchers that go from a treatment of 0 to a treatment of 1 to the outcome evolution of the never treated. And this way you can, under a parallel trend assumption, you can unbiasedly estimate the treatment effect among the switchers in those that become treated. And then you do the symmetric exercise, but for the switchers out, those that go from treated to untreated, you compare their outcome evolutions to the outcome evolution of the always treated. And this way, you can estimate the average treatment effect among the switchers out, and then you aggregate the two things. And so this type of comparison, Diff-in-diff estimator, the DIDM, it's going to rely on a parallel trend assumption that's very similar to this one, except that we assume that outcome evolutions in the counterfactual where the treatment would not have changed for anyone do not vary across groups that had the same value of the treatment at period 1. So that's the difference with respect to that one. So that one assumes that you have parallel trends in the counterfactual of no treatment change or all groups. Here, we're going to assume that we have parallel trends in the counterfactual where the treatment does not change within the subsamples of groups that had the same treatment at period 1. So in my binary treatment case, I'm assuming that all groups that had a treatment of 0 at baseline would have had the same outcome evolution if their treatment had not changed, and all groups that had a baseline treatment of 1 would have had the same outcome evolution if their treatment had not changed. But between those two groups, the trends could be different. And this small difference makes it so that if I combine this, this weakened version of this parallel trend assumption here, if I'm combining it with the standard parallel trend assumption on the Y0, then I no longer have the undesirable feature that the two imply constant effects over time. So this condition here combined with parallel trends on Y0 implies constant treatment effects over time, while the weakening of 8.7 that underlies our DIDM estimator, when you combine it with parallel trends on Y0, it does not imply constant effects over time. Okay, and the DIDM estimator, it can be very easily generalized to discrete treatments. When you have, let's say, a 0, 1, 2 treatments, you're going to look at the groups with a baseline treatment of 0, and in that subsample, you will compare the outcome evolutions of the switchers and stayers, and then you do the same among groups with a baseline treatment of 1, same thing among groups with a baseline treatment of 2, you will aggregate, and you can estimate the treatment effect for all the switchers. And similarly, you can easily extend it to cases where you have more than 2 time periods. You're going to do the exact same estimation strategy for each pair of consecutive time periods, t-1 and t, and then you will aggregate across pairs of consecutive time periods. Now, this type of this estimator will not be valid anymore. Okay, so maybe let me just show it before highlighting the limitation. let me show it in the context of one application. So we computed that estimator on the Genskau et al. Data that we've already used yesterday. Remember, the goal is to estimate the effect of the number of newspapers on political participation. And using a first difference regression, we had found a positive effect that one more newspaper increases political participation by 0.26 percentage point. We revisit this paper using our DIDM estimator, where essentially between each pair of elections, DIDM is just going to look at the counties where the number of newspapers does not change. It's going to look, those are going to be the stayers. It's going to look at the counties where the number of newspapers is changing. Those are going to be the switchers. And then it's going to compare the outcome evolution, the turnout, the evolution of the turnout rate between the switchers and the stayers counties, controlling for the number of newspapers at baseline in the T-1 election, because that's controlling for this is what ensures that the estimator is not implicitly assuming that treatment effects are constant over time. And so then we do this exercise for each pair of consecutive elections, and then we aggregate across all pairs of consecutive elections. And when we do that, we find an effect of one more newspapers of 0.45 percentage point instead of 0.29. So it's a bit larger than with the FD estimator. And it's actually significantly different, not of the same sign, and significantly different from the two-way fixed effect estimator, which in this example is actually negative. So to placebo test the parallel trends assumption underlying our estimator, we can do, like, the standard placebo analysis you would expect, namely, if we have counties that switch with number of newspapers is changing from T-1 to T, and the stayers whose number of newspapers is not changing from T-1 to T, well, we're going to compare the outcome evolutions of the two groups from T-2 to T-1. So one period before the switchers switch. And when we do that, we find a small and insignificant placebo. So it seems that before the switchers experience an increase in their number of newspapers, the switchers and the stayers are not on different trends. Okay, so the connection with the paper I'm going to present is that this type of estimator is implicitly ruling out dynamic treatment effects, in the sense that the control group are all the groups whose treatment is not changing between T-1 and T. But those groups could have experienced a treatment change between T-2 and T-1. And if there are dynamic effects, that change could still affect their outcome evolution from T-1 to T, which could mean that those control groups are actually invalid control groups. Okay, so what we are going to do now is the extension of those static estimators to estimators allowing for dynamic effects. Yes.
What if you control for the treatment? Sorry, what if you control for the treatment history prior to that?
Yeah. You can do that, except that the number of control groups is going to become smaller and smaller. But yeah, you could definitely do that. So one thing okay, so controlling for the treatment history. So the thing we propose is slightly different, is to have a version of the estimator where we still comparing so the treatment groups are going to be the switchers from T-1 to T, whose treatment did not switch from T-2 to T-1. And we're going to compare them to the stayers from T-2, T-1 T. Okay. So if this type of comparisons is going to give you, a valid estimator if the outcome can be affected by the current treatment and the first lag of the treatment. If you want to allow robustness to dynamic effects up to 2 lags, then you need to do the same things, but restricting the comparisons to groups that stay untreated in T-3, 2, 1, and treaters at T versus stayers all along. Okay. Now, treatment history idea, yes, but if you compare groups that have the same treatment history all the way to T-1, and then from T-1 to T, some change, the other one are not changing, maybe the treatment history prior still had some treatment changes, and therefore you need to assume that the effect of those changes are the same among the two groups. So that's still assuming some kind of, it's not necessarily, but it's just that if here, we really are just trying to go to the bottom of this approach of working on the placebo testable parallel trend assumption that do not restrict effects heterogeneity, then under those constraints, we cannot do what you propose. But that does not mean that it's not a valid thing that you can do. And I don't think it's been done, actually. So it's... Okay, so now let's go to the paper. Okay, so what I'm going to present is this paper with Xavier on that's entitled Diff-in-diff Estimators of Intertemporal Treatment Effects. So yeah, I can go a bit quickly, I think, on the beginning, because those are things that we already saw together. So we're going to be using a group level panel to study treatment effects. And here, we don't want to place any restriction on dynamic effects. So YGT could be affected by DGT, but also by GGT-1, DGT-2, etc., etc. And so the standard tool that people use in that case is this two-way fixed effect distributed lag regression, which, as we've just seen, is not robust to heterogeneous effects. So in response to that realization, there's been many heterogeneity-robust Diff-in-diff estimators that have been proposed. And we have seen actually together many of them in this class. We have estimators that are robust to dynamic effects, but that allow for dynamic effects, but they can only be used in the binary staggered treatment case. And there are estimators that can be used in more general designs, like the DIDM estimator I just described, but that estimator rules out dynamic effects of the past treatments on the outcome. So what we're going to try to do in this paper is, if you will, combine some kind of Callaway-Santana estimator with the estimator that Xavier and I had proposed in our previous paper, to have something that's going to allow for dynamic effects and that can be used in general designs. Why is that important? Well, I already mentioned this survey of two-way fixed effects papers that we conducted, where we found 26 highly cited AER papers that were running at least one two-way fixed effects regression. And when you look in details, there are actually only 4 of those that have a binary and a staggered treatment, which means that the heterogeneity-robust diff-in-diff estimators that have been proposed for now are not very widely applicable. So in this paper, we're going to propose heterogeneity-robust diff-in-diff estimators for those complicated cases. And our estimators are going to be widely applicable, even though they are not going to be applicable to any case. Because we are still going to make one assumption on the design, which is that we have at least a few groups that keep their baseline treatment, their period 1 treatment, for a few time periods. And I'm going to highlight some examples where actually this condition might fail. And those estimators are widely applicable because they're computed by our DID multiple GTD and Stata and now our package. We also, but this we actually already did in class, so we don't need to do it. And we're going to revisit Favara and Hans, who studied the effect of financial liberalization on that took place in the 90s in the US on the volume of credit in the economy, and then on housing prices to see if is it the case that the housing supply is elastic enough to absorb an increase in the volume of credit, or actually is it the case that increasing the volume of credit leads to inflation in house prices? And using a technique that we've not discussed actually together, but that's covered in the textbook, it's less commonly used than these distributed lag two-way fixed effects regressions, but it's also fairly commonly used. Those are called local projection regression techniques. And by the way, I think one issue that might actually be more problematic than lack of robustness to heterogeneous effects in this panel data literature is just the wealth of potential methods that researchers can pick from. And in this context, in this example, actually we've tried local projection and distributed lag two-way fixed effect give you completely different results. So I think it's also a contribution of this methodological literature is to discipline a bit the tools that researchers can use in those contexts. And so because you have local projection versus distributed lag, then you can decide to estimate the model in levels or in first difference. That's already giving you 4 specifications that can give fairly different results, etc. And we don't really know which one to use and for which reasons. So using those regressions, they had found pretty short-lived effects of those liberalization. And when we use our heterogeneity-robust estimators, we actually find the opposite. We find that the effects are very small in the short run and they become very large if we believe in our effects, which I'm not so sure we do, but it's more related to potential violations of parallel trends, which would affect also any of those specifications. If you believe in the effects, then actually the effects are small in the short run and then very, very large in the long run. Okay, so we have capital G groups observed at T periods. The groups are typically going to be like geographical entities. We could weight the estimators by the size of each cell, but we are not going to do it to reduce notation. And we're going to assume that the panel is balanced, but our package can allow for weighting, and it can be used with an imbalanced panel. Even though actually dealing properly with the imbalanced panel case is was a bit of a headache. So DGT is going to be the treatment of group G at T. DG is going to stack all the treatments of group G from 1 to T, and bold D will be the design, will be all the treatments of all groups at every time period. Capitalized D will be the support of DG, the set of values that DG can take. And we have this dynamic potential outcome model following Robbins, where YGT can depend on the full sequence of treatments of group G from period 1 to T. So we're going to be conditioning on the design, and here our perspective. I already introduced a bit the cost-benefit analysis justification of our target parameters earlier. Here it's going to be the same. We're going to assume that we are trying to help a planner determine whether the actual treatments bold D that took place were beneficial relative to a counterfactual where all the treatments of every group would not have changed, would have remained the same as in period one, which we're going to call the status quo counterfactual. So we are trying to compare what happened to a counterfactual where no policy would have been implemented, and therefore every group would have kept the same treatment as in period one all along. And so then it's natural to condition on the design in our analysis. But that also implies that our parameters of interest are going to be conditional on the design. They are dictated by the design. They are not it's really like very reduced form of policy evaluation. We evaluate what took place, but there are many other potential parameters we could have wanted to learn, and we're not going to be able to learn them. So a key realization, a key ingredient in our generalization of these event study estimators will be, so remember that in the binary and staggered case, FG was the first date when group G was treated. Now we are going to generalize this definition to FG being the first date, the date when group G experiences a treatment change for the first time. So of course, if the treatment is binary and staggered, the two things are the same. But this new definition is the generalization of the one we had before. So then we are going to make two assumptions, make the following assumption on the design. So we're going to assume that we have at least one pair of groups, G and G prime, such that G and G prime have the same treatment at baseline, and the date at which their treatment changes for the first time is not the same. So we have at least two groups who start in the same in the same value of the treatment, but don't experience a treatment change at the same time. So the first condition could be violated if the period one treatment is actually a continuously distributed variable. If the DG1s are random draws from a continuous distribution, then this condition is going to fail. So that a failure of condition one would not be too much of a problem. In fact, in the paper's web appendix, we extend our estimators to the case where the period one treatment is continuous. And the corresponding extension is actually implemented in our data package that has a continuous option. For now, what I still want to mention is that for now, the extension is a little bit rough in the sense that we just propose a pretty parametric estimator where you need to assume that counterfactual outcome trends under the status quo treatment are a polynomial in that value of the status quo treatment. You could certainly do something a bit more sophisticated, but at least you can already bypass a little bit this requirement. The requirement that you cannot bypass, and which I think is a little bit of a hard constraint on those heterogeneity-robust Diff-in-diff estimator, is the second one. The one that requires that not everybody's treatment changes for the first time at the same period. And this is not a very weak requirement. I can think of many examples where this is going to fail. If you think of the weather, for instance, the treatment being, let's say, temperatures, and your unit of analysis being municipalities and year, you're not going to have a single municipality that experiences the exact same temperature in year one and in year two in your data. So you will have that FG, the date of the first treatment change is equal to 2, period 2, for every G in the sample. Okay? So I think that's a little bit, those are the applications where the heterogeneity-robust Diff-in-diff logic is a little bit breaking down, because to apply this logic, you need to have stayers. And here you will not have, with this type of, very granular and volatile treatments, you will not have stayers. So of course you can bypass this a little bit by saying, okay, I'm going to round temperatures to, sufficient number of digits such that I end up having stayers. But that's a little bit equivalent to choosing a bandwidth. And at this stage, I don't think we're really able to give researchers a very good, no, actually, it's not really it's not the main concern. So, okay, you could define a bandwidth. But then once you've done that, that means that, you're going to have, let's say, 5% of your sample that are going to be such that their treatment change is small enough. It belongs to the bandwidth. And now you can say, okay, those are just as good as stayers. Okay. But then to me, what's more of a problem is that then if you want to do placebo analysis, that means that you would want to compare the outcome evolutions of your T-1 to T units that are within the bandwidth between T-1 and T to those that are outside of the bandwidth between T-1 and T. But for the placebo to be valid, you actually need to restrict the sample such that those units are actually within the T-2 to T-1 bandwidth, because otherwise, so the placebo will compare their T-2 to T-1 outcome evolutions of the quasi-stayers from T-1 to T to the switchers from T-1 to T. But if actually those units, their treatment changed by large amounts from T-2 to T-1, then you're not really, you could have a non-zero placebo estimator, but because of treatment effects, not due to violations of the parallel trend assumption. And then if you start wanting to, do non-parametric, but across 2 consecutive time periods, I mean, yes, maybe you can, in theory, define an estimator that would do that, but it's going to end up being extremely noisy, and you will not have any power to reject to reject the parallel trend assumption. So that's why initially I had the goal of trying to extend these heterogeneity-robust estimators to any circumstance where two-way fixed effect had been used. But here, I don't think it's really, maybe, here, I think that's a circumstance where taking another approach is going to be more fruitful. Okay, so some examples of designs that we're going to be able to cover. So, of course, the binary and staggered one. You could also think of designs where groups get treated and then they exit the treatment at most once. Those designs are pretty common. And actually, not during the talk, but in the paper's web appendix, we highlight an estimation strategy to separately estimate the effect of entering the treatment and the effect of leaving the treatment, because those effects might be fairly different. And that's actually something you can do in those cases using our package. Then you have a small variation on the binary and staggered case, which is the case where groups get treated at different dates with different intensities. So it's combining a bit like heterogeneous adoption with variation in treatment timing. Those type of designs are pretty common, and they can be dealt with easily with our estimators. And then one case that's going to be of interest is going to be the special case where everybody is untreated at baseline, and then anything else, and then anything can happen. And finally, there are cases like the Genskau et al. Application where the baseline treatment is a discrete variable. So we're going to be making a no anticipation assumption your current treatment can depend on your current and past treatments, but not on your future treatments. And then here is the parallel trend assumption we're going to be making. So we're going to be assuming, so it's a generalization of the parallel trend assumption conditional on your treatment at t-1 that we propose for our DIDM estimator in the case with no dynamic effects that I discussed earlier. So here we're going to assume that so this vector, so this potential outcome is the potential outcome that group G would have at t-1 if it keeps its period 1 treatment from period 1 to t-1, okay? So if its treatment never changes. So here we assume that two groups with the same baseline treatment would have the same outcome evolution if their treatment never changes. Okay, so we call this potential outcome the status quo potential outcome, your potential outcome under in the counterfactual where your treatment never changes. And so here we have a parallel trend assumption on the status quo potential outcome. So in cases where everybody is untreated at baseline, then those DG1s are all equal to 0. Therefore, we are back to our parallel trend assumption on the never treated potential outcome, which is also imposed by Sun and Abraham, Callaway Santana, etc. So this parallel trend assumption is different from the one we've seen earlier, only when group treatment varies at period 1. Then, as we did in the case of the strong parallel trend assumption, in the case of the parallel trends, if group treatment does not change between period 1 and 2, we want to see if this assumption restricts effects heterogeneity when we combine it with the parallel trend assumption on the untreated outcome. And the answer is that it does, to some extent, but it does not assume homogeneous effects. It assumes that when you combine the two assumptions, what you end up assuming is some kind of parallel trend assumption on the treatment effects, which is not at all a weak assumption. It means that groups treatment effects should evolve in parallel. It's not only their untreated outcome that should evolve in parallel, also their treatment effects. But at least we are not assuming totally homogeneous effects. While if you were to assume that this holds unconditionally, even for groups that don't have the same value of their baseline treatment, then when you combine that with the parallel trend assumption on the never treated outcome, you can actually show that this is ruling out dynamic treatment effects. This is actually assuming that your past treatments do not have an effect on your current outcome. Okay, so this is not an innocuous assumption. When you combine it with the standard one on the Y0 outcome, you're effectively assuming parallel trends on the treatment effect. That's strong, but it's still much weaker than making an assumption that's effectively ruling out dynamic treatment effects. Okay, so what are going to be the target parameters and the estimators? So as you're going to see, here it's really going to be a paper about target parameters, because once we've defined our targets, it's going to be very easy to propose estimators. So first, we're going to let for every G the last date where there is still a group that had the same treatment as G at period 1 and whose treatment has not changed yet. Okay, so that's the last period where we still have a valid control group for group G under valid control group under our parallel trend assumption. And then we're going to let delta GL be, so delta GL, so, we've changed notation between the papers and the textbook. That should be a TEGL in the notation of the textbook. That's the difference between the actual outcome of group G at period L and the counterfactual status quo outcome that group G would have had if its treatment had never changed. So that's why we call it the actual versus status quo effect. So to unbiasedly estimate this quantity, we can just use a simple Diff-in-diff that's comparing the outcome evolution of group G from the period just before it experiences its first treatment change to L periods after that, to that of control groups with the same baseline treatment as group G and whose treatment has not changed yet at Fg minus 1 plus L. So we replace Fg. Fg was the first treatment date. Now it's the first switch date, the first date when your treatment changes. And we were using the not yet treated as the control group in the binary staggered case. Now we're using the not yet switchers as the control group, conditioning on the baseline treatment. And we can show that this estimator is unbiased for the actual versus status quo effect. So now let's see if those effects, those actual versus status quo effects, identify things that are meaningful or not. They may not always give us things that are easily interpretable. So if you think of a group whose treatment trajectory is that they start at a baseline treatment of 1 and then they go to 2 and then they go back to 0, then this AVSQ effect is comparing their outcome under treatment sequence 1 to 0 to what they would have had under 1, 1, 1. And this is an effect that's a bit tricky to interpret because that's an effect of decreasing your current treatment by 1 unit while increasing the first lag of your treatment by 1 unit. And you could have that increasing the current treatment and the lag treatment both have a positive effect on the outcome, but yet because this is mixing an effect of an increase and an effect of a decrease, this ends up being negative. So we're going to rule out the existence of such treatment sequences. We are going to assume that it's kind of a no crossing condition. We're going to assume that if your treatment sequence is such that either you're always weakly above your baseline treatment or you're always weakly below your baseline treatment. If so, that restriction, for instance, I've not checked, but I'm pretty sure that it's violated for at least some groups, some counties in the Genska et al. Data. When it is, our state command automatically drops the groups that fail to satisfy this condition. And unless we still have an option to allow you to keep them if you want, but we would not recommend keeping them because the treatment effects for those cells are very hard to interpret. Okay. So then how can we aggregate those effects? So we're going to propose to aggregate them by we're going to propose to just average them, but we just need to make sure before we average them to multiply those AVSQ effects by -1 for the groups such that their treatment path is always below their initial treatment. Because for them, the delta GL effects are actually effects of being exposed to a weaker treatment. Yeah, those are effects of decreasing the treatment. And so to make sure that we are not averaging together effects of increasing and effects of decreasing the treatment, and that's why we multiply the effects for those GL pairs by -1. And in this way, we have that the delta L effects, so they remain a pretty reduced form effects, but at least they can be interpreted as effects of having been exposed to a weakly larger treatment for L periods. And then to unbiasedly estimate them, we just average our DID GL estimator that we had earlier. So the interpretation of those non-normalized event study effects is a little bit complicated. So in a binary stagger design, simple. Delta L is just the average effect of having been exposed to the treatment for L periods. But in those designs I was mentioning, where groups can enter and leave the treatment at heterogeneous dates, you're going to have that those delta GL effects identify an effect of having been treated for a number of periods that could differ across groups. So you could have groups that get treated for 2 periods, others that get treated for 3 periods, etc., etc. So you're going to be aggregating effects of heterogeneous exposures to the treatment. And also, for the groups that at the time of measurement have already left the treatment, the recency of the treatment could vary. You could be aggregating an effect of 3 periods of exposure, but where exposure stopped 2 periods ago, with an effect of 4 periods of exposure where exposure stopped 1 period ago, etc., etc. Okay, so that's a little bit what complicates the interpretation. So, of course, one thing you could do would be to estimate, and actually we have an option in our data command would be to, if the number of treatment paths in your data is not very large, if the switchers can be divided into 4 categories, you have those that do 0, 0, 1, 1, 1, 2, 1, and then you have another category that does 1, 1, 2, 2, 2, 2, and so on and so forth. Then you could estimate path-specific event study effects to make sure that you separately estimate the effect of the first trajectory and then the effect of the second trajectory, etc. So that's obviously something you can do. But the designs we have in mind are more complicated designs where you have many paths, and therefore trying to estimate separately the effect of each path is a bit hopeless. So here I just want to make one aside. Yeah, to compare a little bit, to do a bit of a comparison with the existing estimators. So when all groups have a baseline treatment of 0, when there is no variation in treatment at baseline, this DIDL estimator that we propose can be recast as an estimator that you could can be recast as an estimator a la Callaway and Santana, where you redefine the treatment as an indicator equal to 1 if at period T, group G's treatment has changed at least once. So you binarize and stagerize the treatment. The treatment might not be binary and staggered, but you make it binary and staggered by redefining it as having experienced at least one treatment change. When the treatment at period 1 varies across groups, applying estimators at la Callaway and Santana with this binarized and staggerized treatment will not give estimators that are numerically equivalent to ours. And actually, it's something that we started seeing being done in applied papers, that will not give estimators that are the same as the one we propose. And the intuition is just that our estimator is comparing switchers and stayers with the same switchers and not yet switchers with the same period 1 treatment, while this naive extension of the Callaway-Santana estimator is comparing switchers and stayers without conditioning on the baseline treatment. And like I said earlier, implicitly, the parallel trends assumption that you need to make when you compare switchers and stayers that do not have the same baseline treatment, that's going to implicitly assume away dynamic effects. Okay, so that's actually a very strong assumption. Okay, but so we might not like the fact that those non-normalized event study effects aggregate together effects of very different treatment trajectories and could then become hard to interpret. So can we do something about that? Yes, we can, even though, it's not going to be perfect. But we can try to, essentially, the goal is going to find a somewhat meaningful way of normalizing those estimators. And the normalization problem is more difficult when you have dynamic effects. So when you don't have dynamic effects, when your potential outcome function only depends on one variable, the current treatment. If you have a non-binary treatment, well, you could be able to estimate a y2 minus a y0 for a group. Well, you just need to normalize that by 2, and that's going to give you a slope that's pretty easy to interpret. Now, the issue is that with dynamic potential outcomes, we're looking at potential outcome functions that can depend on several arguments. So the normalization that we propose is the following. We normalize the delta GLs by this quantity here, which is the sum of the difference between the treatment that group G got at period FG, the first time when its treatment changed relative to the baseline treatment, plus its treatment at period FG plus 1 minus its baseline treatment, plus its treatment at FG plus 2 minus its baseline treatment, etc., etc. So, for instance, if we have a group that started at 1 and then went at 2 and then 3 and then 1, we would be not. So the event study effect 3 periods after the first treatment change is going to be normalized by 2 minus 1 plus 3 minus 1 plus 1 minus 1, 0. So we're going to normalize it by 3 with the idea that at period 4, it's been exposed to 3 more treatment units than it would have been under the counterfactual scenario where its treatment would never have changed. Okay, so that's the idea of the normalization. It's a simple idea, but if you look on the archive where you can see all the versions of the paper, it took us, I think, 6 versions of the paper to arrive at the conclusion that this was like a reasonable normalization in this context.
Right.
Yeah.
Just to understand if I got it. So this is the amount of changes in units of treatment change?
Yeah, exactly.
Okay.
Cumulated. Yeah, exactly. So why is this a reasonable normalization? Well, that's because of this lemma here, which, despite the ugly notation, is not that difficult. So this is the slope of the potential outcome function of group G at this date, fg minus 1 plus L. When you switch the kth lag of its treatment from the status quo DG1 value to the actual treatment of that group at fg, k periods before fg minus 1 plus L. So it's a slope with respect to the kth lag of the treatment. And so what we show in this lemma is that actually this normalized actual versus status quo effect is actually a weighted average of the slopes of the potential outcome of G at fg minus 1 plus L with respect to the current treatment, with respect to the first lag of the treatment, etc., all the way to the L minus 1th lag of the treatment. And the good thing is that the weight that we put on each slope is identified. Okay, we're going to be able to compute that from the data. And so then we can just, of course, we are not going to be able to estimate G-specific effects, so we're going to aggregate that across groups, and that leads to a normalized event study estimator L that's computed by our command when the normalized option is specified. So we're going to have that those normalized effects, they estimate weighted averages of the effect of different lags of the treatment on the outcome. And the weights that they put on each lag can be estimated. And there is actually, we have an option in our command to show you the weights. So for the first event study effect, it's easy. It's only an effect of the current treatment on the outcome. But for the event study effect number 2, it's going to be a weighted average of the effect of the current and of the lag treatment on the outcome. And you may want to know whether you're putting 90% of the weight on the current and 10% on the first lag. That's going to help a little bit interpret the effects. And so we recommend actually reporting those weights. Now, in relatively simple designs where weight treatment can change only once, the weights have a very simple expression. They're just equal to 1 over L. So that means that event study effect 2 is a weighted average of the effect of the current and first lag of the treatment with weights a half. If event study 3, normalized event study 3 will be a weighted average of the effect of the current treatment, effect of the first lag, effect of the second lag with weights a third, etc., etc. So you see that the further you go alongside the event study function, the less weight you're putting to the effect of the current and recent treatments, and the more weights you're putting onto effects of of older treatments on the outcome. And so if it is the case that, which might be realistic to assume that current treatments have a larger effects on the outcome than older treatments, you should see that this normalized event study function is declining. Okay. Okay, so that's the baseline. So then all the extensions. So we derive inference results. We show how to do pre-trend estimators, and that's implemented via the placebo option in Stata. We allow, even though, like I was saying, for nights, it's the extension is still a bit parametric, not fully developed. We still give you something that you can do if your period 1 treatment is continuous. We have an option to allow you to control linearly for covariates, and that's the controls option. We have an option to allow you to have group-specific linear trends, that's the trends-lean option. We have an option to allow you to control non-parametrically instead of linearly for covariates, provided they are, discrete and taking a small number of values. So that can be useful for instance, to have like industry-specific trends in a firm-level analysis or state-level trends in a county-level analysis. And we also allow you to do a bit of heterogeneous treatment effect analysis by allowing you to compute, to estimate the best linear predictor of treatment effects given a number of covariates with this predict at option. Okay, so to finish an empirical application, so those financial liberalizations that took place in the 90s in the US. So what I did not know is that prior to the 90s, prior to 1994, the US was not an integrated financial market. The banking market was at the state level. And that ended in 1994, but that did not really end in 1994 because at that time, states could still impose 4 different types of restrictions that would make it difficult for a bank from, let's say, Florida to start operating in Nevada. And gradually, states lifted those 4 restrictions, and so we can define a treatment variable, which is the number of restrictions lifted by state G at year T, which is going to range from 0 to 4. So it's a little bit weird to aggregate those, qualitatively different regulations into an ordinal measure, but that's what is done in the finance literature. So we just follow what others have done. And so the paper is using county-level data from 1994 to 2005 to estimate the effect of the number of regulations that are being lifted on the volume of credit in the economy, so the mortgages that are being originated by banks, and the growth of house prices. So they estimate those local projection regressions that we did not discuss together, but that I'm going to briefly explain. So the idea of those regressions is to regress. So that's a technique that's coming from time series in a seminal paper by Jorda, where there the idea is to estimate an impulse response function. You're going to regress leads of the outcome on a shock that takes place at period T. And these techniques have been imported into the panel data world. And there, what people do is that they estimate, they regress the lead of the outcome on G fixed effects, period fixed effects, and the treatment DGT, which here is the number of deregulations in county G and year T. And also, the regression is estimated in log and inverse difference. Okay, so actually I can even run the demo. Up. No. Inflate. Ah, yeah, it's because of the. Yep. You. Okay, so now I've loaded the data and I can compute my non-normalized event study estimators.
Let's check. Yep. No, most. Yep.
So you see that's the event study graph I get. So for the placebos, even if I look at only 3 placebos, I already have a relatively small sample size. But if I were to try to estimate 4, I would get a very, very small sample size. So that's one of these cases where, because most of the states that adopt those, that deregulate, do so very early on in the panel, I can only compute a small number of placebos. So, following the rule I gave you at the beginning, I should not be computing 8 event study effects. I should probably stick to 3 event study effects here. Here, I'm just following what the authors estimate actually with the local projection, they estimate 9 effects. If I try to do that, I'm going to end up with the 9th effect estimated out of like 5 counties. So I'm not showing it, but that's why I show so many effects. But so keeping that in mind, that's certainly not the most convincing event study graph you can think of, in the sense that the placebos have pretty broad confidence interval around them. And it's only in the very long run that you start to see actually marginally significant effects appearing. Okay. But at least the conclusion from the local projection regression that the effects are quickly disappearing does not seem to be to really be there.
Right?
Yeah.
I look at this. If I look at this graph, to me, it would seem like just a linear trend.
Yeah,
exactly.
You can fit a linear trend in here. The one that's a bit more convincing is this one for the house prices, which okay, let's see if I have the code for that one. Yeah, that's this one here. That one is a little bit better, but again, there is still the concern that I'm only able to, so this one first is not trivially small. And, after 3 periods, I start seeing a little bit of an effect, but it could be rationalized by differential trends I could fail to reject. And on top of that, so then I have very, very large effects in the long run, but, in the long run, I don't know. But so it's a bit orthogonal to, fortunately for us, our paper was more about, heterogeneous effects and than about differential trends. But yeah, I don't think this would pass a very scrupulous test of whether the trends are differential. But when it comes to robustness to heterogeneous effects, what's interesting is that the local projection is telling you, okay, large short-run effects and then no effects in the long run. And that's exactly the opposite of what we find. And when we normalize the effects, if you remember, if lagged treatments tend to have less of an effect than the current treatment, we should see that the normalized event study function is declining, We see a little bit of that for the first outcome, but even then it's not very clear. And we see actually the exact opposite for the housing price outcome.
Sorry, you just made once again differentiate the interpretation between the normalized and non-normalized.
So the not normalized, the interpretation is just that's an average effect of having been exposed to a weekly larger number of deregulations for a number of time periods without controlling what was the number of deregulations you were exposed to, for instance, or how recently those deregulations were passed. This has a slightly more structural interpretation as a weighted average of, so that one, and actually here the assumption that group treatment is changing only once is almost satisfied. And there are a few states that they regulate more than once, but very few of them. And so in that case, we know that that one is an effect of the current treatment on the outcome. That one is an average with weights a half and a half of the effect of the current and the lag. The one after with weights a third of, so and so forth. And then, of course, we would want to do we cannot quite do what the distributed lag regression was giving us, like separating the effect of the current and the first lag and the second lag, etc. We can just, if we are not willing to impose very strong assumptions, we can just estimate weighted average of those effects without being able to tease out what's due to the current, what's due to the first lag, etc. But that's the at least the best we were able to do in that paper. Okay, and so I would just want to mention one last thing about those local projection regressions, which is that you should never use them. At least the very naive, like the not very careful way that people have imported the Jordan idea into the panel data context. So what I'm going to say, okay, so has nothing to do, like I have nothing to say about Jordan's local projection method in the time series context, but the way people have done it in the panel data context is extremely strange because, they regress the lead of the outcome on the treatment. So essentially, this is comparing the lead of the outcome for people that are treated at T versus those that are untreated at T. But the issue is that you might very well have some units that were untreated at T and became treated at T+1 or at T+2, etc., so that at T+L, they are effectively treated. And because of that, you're going to have that we have a result showing formally that the coefficients on the treatment in this regression, they identify weighted sum of treatment effects. You would hope to estimate an effect of being exposed to the treatment for L periods. Well, unfortunately, you have contamination. You're estimating weighted sum of the effects of 1, 2, 3, L, etc., L plus 1 period of exposure to treatment. But the feature that's really unique to these regressions is that actually the weights do not sum to 1. So that's in this sense that I think you should never use those regressions because, two-way fixed effects, you can rationalize why you could use them because if treatment effects are homogeneous, that's a fine method to use. And actually, it's even giving you an efficient estimator. But here, even assuming homogeneous effects, because the weights sum to less than 1, you're going to have that the coefficients are actually could be biased towards 0. And it's even worse than that because actually for some of those, so we compute the weights attached to those regression. And I think it's starting at, okay, let me see if I have it here. Yeah, it's starting at the 4th coefficient. So starting at this coefficient, actually you can show that the sum of the weights is negative. So you're estimating a weighted sum of effects where the sum of the weights is negative. So even you could have sign reversal even under constant treatment effects. And so that's probably explaining. So, I'm not saying that this is the ground truth about these, the effect of those deregulations, but the fact that this graph, starts with some effects and then has no effect anymore, could just be due to the fact that the more you progress, the more negative the weighted sum of effects become, and so you're biasing the whole thing towards zero at the end. Okay, and now so there's been a much more careful adaptation of the local projection method to the panel data context by Jorda, Dubé, etc., and co-author. If you're going to use local projection, you should be using that version, not the naive one. That's still pretty common, actually. It's not, it's not the only example that you can see. For instance, in finance and trade, etc., you see many examples of those regressions. Okay, so that concludes the talk and the course. Thanks very much for your attention.
Thank you to you for all the class, and it's been amazing to have you here. So if there are questions.
One question on the normalization. So this is a sum. So the order in which different switches happen does not.
Yes.
Did you consider to, like you said that you tried many others, something in which the ordering matters because cumulative, like within dynamic effects, cumulative effects are a subclass of dynamic effects, maybe, in which it's important. For example, again, relating to temperature, a few epidemiologists have been interested in whether there is a specific heat wave effect as opposed to exposure to heat daily, let's say, but in days in which allows people to recover a bit, So, and then some economists said, okay, maybe to control for this, we can have accumulation rules in which there is relief.
No, or you could have like a discount factor, or something like that. No, when I was saying it took us a long time, we were thinking of much simpler things. But that's definitely a good idea. The only issue is that you're going to need a model to justify how you aggregate them. But in cases where again you have like a good biological model of how the response function, how the response is with respect to various lags of the treatment, you could definitely do that indeed. But that's a good point that, for us, if an increase of the current treatment of 1 and the lag treatment of 2 will lead to the same normalization, but but one caveat to this is that this weighting function that I was showing you will show you that in the 1-2 case, you're putting less weight on the current treatment than in the 2-1 case. That's the usefulness of this of plotting this weighting function. Okay. Yes. Questions?
So thank you again.